Hey guys, welcome back to the hptuners live training seminar. My name is Alex Peitz of Peitz Performance, and I'm going to be your instructor for today. Today, we're going to be discussing PD blowers and all things related to PD blowers. It's going to be pretty awesome because we're also sitting inside of a 2012 Dodge Challenger SRT8 with a 6.4-liter Hemi, which we have put pistons and rods here at our shop, and also one of our custom cams that we offer for this particular application, as well as a Whipple 2.9-liter supercharger. So you guys are going to get a real-life demonstration of what the data looks like coming from this car, and we're going to discuss some of that and break some of that down so you guys can hopefully get a better understanding of some of the intricacies that go into tuning one of these vehicles with this type of setup. Now, we're going to be talking about the Hemi. However, you can apply this methodology or this information to pretty much any vehicle, car, truck, what have you, with a PD blower. All right, so it's going to be pretty awesome. You guys be sure to stick around because towards the end of the class, we are going to be having our quiz, which we usually do, where we're going to be asking you one question, and the first person to answer the question correctly is going to win an MPVI-2 loaded with 2 credits. So hopefully you guys at home can get going with all of your tuning stuff and start having some fun and joining us in the tuning world. So it's going to be pretty awesome. And without further ado, we're going to get right into it. All right. So like I said, we are sitting inside of a 2012 Dodge Challenger SRT8. To give you a little more information, again, it is still 6.4-liter. We have not put a different crankshaft. It is a stock crank, but it is fitted with manly pistons, manly rods, and the Whipple supercharger. It's making about 7 pounds of boost right now. It's on 93 octane. Also does have long tube headers, if I'm not mistaken. And we also have, an overdrive pulley on the lower and also a slightly smaller upper pulley as well. So it makes pretty good power. We're gonna see what it makes right now. It's gonna be pretty cool. So it's let's get going on it. So first things first, we're already on the dyno. We're already strapped down. We're ready to go. I've got the VCM scanner opened up on my screen, which you guys should be able to see here. And also I have the dyno set up. I've got the customer's information inputted into the dyno already. I've also already set the RPM. We are using RPM from wheel speed. So I let the converter lock. I put it in 3rd gear. This is a NAG1. This is not an 8-speed. So it's a 5-speed transmission. I typically do the pulls in 3rd gear as opposed to 4th, just to keep the load down and keep the length of the pull as, not short as possible, but keep it shorter so we're not just lugging the engine a bunch. So just keep that in mind. So let's go to the Dyno software. So let's pull it up here. In case you guys don't know, I do have a Mustang Dyno MD800. It is an all-wheel drive dyno. We're just in 2-wheel drive right now. It does have dual eddy current brakes. So we have PowerDyne opened up, and now we're going to go to our test, and we're going to go to performance. We're going to set that to power curve. Okay, so this is where we set our sampling RPM window. So we're going to start sampling at 3,000 RPM, and we're going to end sampling at 60, let's say 6,400, actually 6,300, just in case. So we could go higher, but I'm just trying to do this for demonstration purposes right now. This car actually makes pretty good power, even a higher RPM. So just keep that in mind. All right, so we got that set. You want to make sure that you have simulated inertia active. And let's see here. We have simulated inertia active, vehicle simulation on, RPM limits are on. So we should be ready to rock and roll, guys. All right, so now we're going to go back to the VCM scanner. And first things first, we're going to go 2 presses on the button to go ignition mode for run. Then we're going to connect to vehicle. And I'm using my Dodge channel config. If you guys need a Dodge channel config, hit me up, Alex at PeitzPerformanceTunes.com. I can also email this to you so you have a channel config to get started with. More than happy to share that with you guys. All right, so we are connected, and now we're going to click Start Scanning. All right, so we're getting data. Everything's looking correct. Coolant temp's 165. IAT just sitting here is 136. That will go down as we do the pull, actually, because we just have stagnant air right now where it's reading that. We are reading AFR via an AEM wideband, which is going into the can. So it works pretty well. It's very quick. You know, there's all kinds of other widebands out there you guys can use, but this is just the easiest for demonstration purposes, and it works really well. So nonetheless, let's go ahead and fire it up, and let's do a pull. So give it a second here, kind of idle down. And the wideband is in the tailpipe, so it reads a little bit leaner right now because we're not getting as good of an exhaust signal at the tail. But once we get into wide open throttle, it's pretty much the same as if you were in the collector. It'll read slightly leaner, but if you tune for the leaner mixture all the time, it's all relative basically. So we'll be all good, just in case you guys are wondering why it reads so lean. In that scenario, if you do have the wideband in the tailpipe, what you really want to focus on is your primary O2 sensors. They're oscillating properly. So that means that we are bouncing right there between 14 and 15 parts air to 1 part fuel. And our fuel trims are pretty good. It oscillates a little bit, changes a little bit as it heats up. But our fuel trims, you know, we want to be plus or minus 5% if possible on the long term. Short term will vary some. All right, so we should be ready to go here. So we're going to go ahead and get rocking on it. All right, so get back to the dyno screen. All right, actually, we're going to keep you guys in the VCM scanner so you guys can look at that. All right, that was fun. Had a little kick to it there. All right. Hey, Lane. Lane. Say out that you're in the shot. We're taking video from right there. Sorry about that. Um, anyways, all right. So let's see what we got, guys. All right, so we went wide open throttle right about 3,000. There's a little bit of a transitional period there. So right at 3,500, we're looking at 11.6 air fuel, 11.6, 11.5, 11.4, 11.5, 11.6. Looking pretty good there. Spark advance was 14 degrees. And let's see what we made for power. So let's go back to the dyno screen. All right, so it looks like 582 horsepower and 540 pound-foot of torque. Just to give you guys a little bit of reference on this, a stock 392 on my dyno makes about 395 horsepower, especially the nag ones. Sometimes they'll make a little bit less. Again, we are in third gear as well. We're making about 6 pounds of boost right now. So we're not trying to turn the earth with this particular combo. Once we put E85 to it, it picks up like 100 horsepower. But this is just as kind of getting around street daily tune, if you will. So not really putting the screws to it, so to speak. But yeah, good, reliable horsepower. Couldn't ask for a better, looking graph. It looks pretty good, and everything's looking good. So we're gonna come back to this when we talk about the tuning considerations for PD blowers. I just want to get you guys started off with a bit of a bang, get you excited about this, and we'll come back to it. All right, so now we're actually going to discuss the benefits of PD blowers, and we'll go from there. So first and foremost, what is a PD blower? Well, that just means a positive displacement supercharger or a positive displacement blower. And that's typically a blower which sits atop the motor and takes place of the intake manifold, so to speak. So within that, you have different types of PD blowers, of course, which we will discuss that here later on. But generally speaking, the PD blower is going to be extremely helpful because anytime that you can put compressed air or boost into your motor, you're going to introduce more oxygen and more air charge and higher cylinder pressure, which typically will generate more power. Of course, when you do that, you have to account for that with additional fuel, which we'll discuss that here a little bit later on in the seminar. However, that's the biggest advantage. Obviously, we're going to make more power because we're packing airflow into our engine, which is also awesome, right? So can't go wrong with that. Now, some other advantages of a PD blower versus maybe a centrifugal supercharger is the fact that you're going to generate boost right off the bat, right when you go wide open throttle and that bypass valve shuts, you're going to be making boost, which means you're going to be making torque right off the line. And as long as you can manage that torque and actually generate traction and not just wheel spin, you're going to go a lot faster. The acceleration rate's going to be much greater and it's going to be awesome. But the issue is managing that and being able to get traction. So then you really put a lot more load on your suspension and everything else and chassis tuning of the vehicle. So there's a lot of things you have to take into account when you go to do that. So sometimes in certain applications, it may be better to use a centrifugal supercharger or a turbo or whatever it may be. But again, a PD blower is going to give you many benefits. Also, it looks pretty cool under the hood. From a installation standpoint, a PD blower or PD supercharger is typically easier to install because you don't have to run piping, and basically it's just a nice fitment under the hood because it's just right there in place of the intake manifold, and you can run a filter and intake tube going into the supercharger, and it's a pretty straightforward process, right? So just keep that in mind, guys. When you're going to figure out, do I want a PD blower, do I want a centrifugal supercharger, or do I want turbos or whatever it may be? So hopefully that helps give you a little bit of insight on that. So within the PD blower, you have a root style supercharger and you have twin screw and sometimes a hybrid of those. And we'll talk a little bit more in depth about that here in a second. Now let's talk about some of the disadvantages of a PD supercharger. One main disadvantage is the fact that you are driving that supercharger with a belt. You are now reliant on that belt to do its job every single time you go wide open throttle. Sometimes that does not happen. And if you have, as we call belt slip, you have a reduction in boost, which if you have a reduction in boost, you guessed it, is probably a reduction in power. So you have to make sure that you have a good belt, that you have your tensioner set up properly, and that's working all the time. So there is additional maintenance that's involved if you want a PD blower on your car. But as I always tell everybody, more power equals more problems. So that's just something you have to keep in mind and account for it whenever you can, however you can. All right, so that's the main disadvantage, I guess, of a PD blower. Some other disadvantages of a PD blower versus a centrifugal supercharger is just that it's going to be hard to get traction, and also the drivability is usually pretty good, but on some cars, some applications, that bypass valve being there and that kind of phenomenon which occurs when that bypass valve shuts, which we'll talk about here in a second, that can create somewhat of a surge. You also kind of saw that here, even on this car, going to wide open throttle. It surged a little bit once the bypass valve shut. It kicked me back, and it wasn't as smooth of a transition as, say, a turbocharged application would be, or even a centrifugal supercharger. Now, it's not usually that pronounced, but just happen to catch it at the right scenario, pretty much for that. So just keep that in mind, that you may experience different drivability issues depending on your application. Now, some of the older Dodge platforms, like I'm sitting in right now, are harder to get dialed in, and there are external controllers, I guess you could call it, such as like Smooth Boost, which can basically be an electronic bypass valve, which can alleviate some of those issues if that is a problem you are facing. So there are ways around that, and so it can help. But I just want to keep that in mind, guys. Now, if you look at a Hellcat, for example, the Hellcat has an electronic bypass valve. So that helps substantially in aiding in some of that surge effect that you'll feel when that bypass valve shuts. Because once it shuts, it's just all the boost right now, right? Now, you guys may have, you guys been around a long time. You've seen some of those kits out there. I think like one of my buddies had a Volkswagen one time, and he had a supercharger on that, and that thing didn't even have a bypass valve. and it was making boost at idle, and it was just rowdy, a rowdy little thing. It wasn't definitely was not ideal. So just keep that in mind. Some of the effects you can have with differing offerings out there. So all right, so PD Supercharger setup considerations. Before I move on, anybody have any questions? It'll take about 30 seconds. Anybody has any questions? Hmm. So some of you guys are asking about the necessity of an intercooler if you're running E85. So even with E85, I highly, highly recommend having an intercooler because the E85 is only going to do so much in terms of cooling the combustion temperatures. It will do that because it is packing additional oxygen and it is much greater fuel mass. So you're putting more fuel to air in that scenario into the engine. And so, yes, that does cool the combustion some, but also you need to cool the air charge. So all of your PD blowers are going to have, and I'm glad you guys brought that up actually, because all your PD blowers are going to have a brick typically inside or below the compressor housing, basically. So that brick is like an intercooler. Well, it is an intercooler, but when most people think of intercoolers, they think of external intercooler, like air-to-air intercooler in a different application like turbo or what have you. So in this particular case, you have a brick or intercooler below the housing, and then you have a heat exchanger external from that, which actually allows airflow to go across it while coolant, supercharger coolant, or any type of other liquid is flowing across the other way, and that's actually cooling the air charge because that's going into the brick, and then that's cooling your air charge in below the supercharger. So I really think in any application you really need that effect to be able to aid in cooling the air charge temperatures because the higher the air charge temperatures, the higher the likelihood that you're going to see pre-ignition or detonation, and that's really what we don't want. So I really recommend intercooler and E85 because it's a great combo. I, yes, sir. So another great question with heat soak. On heat soak on a PD blower car, you're more likely to see that effect of heat soak, right? Basically, that's just that because that blower is sitting on top of the engine, it's going to kind of resonate to the rest of the engine more so than if you have your head unit, centrifugal supercharger, for example, is external from the engine. So yes, it's generating heat, but it's able to essentially dissipate and it's not sitting on top of the engine. So you do have some native benefits to having that centrifugal supercharger versus having the PD blower sitting on top of the engine. However, if you have a good intercooler system, that's really not as big of a problem as you would think it would be, especially like some of your root style superchargers out there. They're much more thermal efficient. Like Magnuson is very thermally efficient. Harrop also, and that depends on their brick design. But some of those superchargers have very good thermal efficiency versus some of the other superchargers out there that are maybe larger and displacing more air. But the thing about that is the more air you displace, the more pressure you make, and the more pressure you make, the more heat you generate. So you have to be able to manage that heat a lot. And that actually brings me to another point real quick. Another advantage of the PD supercharger is the fact that whatever air that PD supercharger can displace, that's basically like putting another engine on top of your engine, so to speak. Let's say you have a 5-liter Coyote and you have a 2.9-liter supercharger. Well, now you have 7.9 liters of displacement versus 5 liters. So that's the general idea behind it. Just like, the C7 Z06, for example. So you had a big cubic inch C6 Z06, 427 cubic inches. With the C7Z, you only had a 6.2 liter engine versus a 7-liter engine, but it made more power because it has a supercharger on top of it. But I know you guys are thinking already, the C7 Z06s have a lot of heating issues, and they do, and that's a great comparison to kind of go back into our discussion what we're talking about right now. However, I did have a C7 Z06. It was a 2017. They had improved the brick design. They improved the lid design. They improved a lot of things about that. And I personally never had reduced engine power running my car on the track, doing sessions for 20 minutes or so, even more sometimes, longer sometimes, in the middle of July at Pikes Peak International Raceway. So there are ways to mitigate those issues if you have proper setup to alleviate them. So hopefully, hopefully that answers you guys' questions. Anything else? Okay, yeah, so we'll move on, guys. All right, so PD Supercharger setup considerations. So we've actually kind of been talking a lot about this already just by nature of our conversation, which I love the input, guys. It's great, great conversation. So some other setup considerations. We want to make sure that we have a proper belt. And by saying that, I really mean, do we need a 6 rib? Do we need an 8 rib? Do we need 10 rib? Do we need 11 rib? You know, some superchargers, some setups require more ribs because you're generating more pressure, you're generating more RPM, and you're going to have a much higher likelihood of belt slip. Also, you know, if you look at any of your OEM platforms that come with a PD blower, they're going to have a dedicated drive system on the belt. So they will have a separate 8 rib, 10 rib, or 11 rib, you know, a ZR1, for example. They'll have a separate setup for that, right? So you're just driving the supercharger with a pulley, which is affixed to the balancer, and then you'll have an idler and a tensioner, and then your supercharger pulley. So it's a much better solution than actually sharing with all the other accessories on the engine, because now, you know, if you lose a belt, you lose everything. But also the 6 rib is much more likely to slip. And if you can't get a dedicated drive system, you would have to actually change your pulley, change your water pump pulley, power steering if you have it, if it's mechanical power steering or hydraulic power steering, so on and so forth. So depending on what you're going to be doing, you have to think about that stuff ahead of time and think about the realistic goals you have for power and think, okay, I need to spend money on, you know, a better heat exchanger. I need to spend money on going to an 8 rib or 10 rib dedicated drive system, or changing out my accessories to 8 rib so I can make more boost and have less problems. So those are all things to think about. In addition to that, we talked a lot about airflow. We talked about cooling. We talked about, you know, packing more oxygen in the cylinder and managing air charge temperatures, but we haven't talked about the fuel supply, right? So whenever you make more power, it requires more fuel. So you have what's called brake-specific fuel consumption. Now, in a naturally aspirated scenario, it's like half a pound per hour per horsepower required to fuel your engine, right? On a PD supercharger, it's about 0.55 to zero point 0.6 pounds per hour per horsepower. So you're talking about more fuel consumption, therefore more fuel flow required to make the power you need to make. So that's another consideration you have to take into account. So when we're going to figure out what fuel we need to supply it with, we need to know there's a lot of calculators out there, but you can type in, you know, rough your horsepower, what you're going to make at the crank, and it will tell you the fuel flow required, but it will also tell you what injectors you need. You're going to take that fuel flow required divided by 8, basically, if it's 8 cylinder, and that'll tell you what size injector you're going to need roughly. If you don't want to go above a certain amount of duty cycle, it'll also tell you fuel flow required will tell you what size fuel pump you need, right? But that's only part of it, right? Also, the size of the fuel line, the feed and return, will also have an impact on how well that pump is going to do for you in this situation. So also, another thing I highly recommend whenever you're going to add fuel to the car, because you've added boost, you really should get a regulator and a return and run it back to your tank, because that way you don't have as much head pressure, you're relieving pressure, but also you're adding 1 pound of fuel pressure per 1 pound of boost. So it keeps your pressure drop consistent across the whole RPM range at wide open throttle. So if you had, you know, 58 psi at the rail and 48 psi at the intake manifold, you have 10 psi of pressure drop there. So you want to maintain that pressure drop all the way through, so it makes your tuning that much easier, right? So I'm just giving you basic examples, but just generalizing things. But that's just to get your mind flowing and thinking about that, right? So we have a, okay. All right. So you guys are asking about a cog versus a belt pulley. That's also a good, yeah, cog setup versus your traditional ribbed pulley. That's a really good question. Cog is awesome, and if you can do it, great. However, it is typically more expensive and you're talking more race car at that point, right? So you could definitely do it for sure. It's just your typical customer, if you guys have shops or for yourself, they're usually not going to want to invest that kind of money. But it does work well if you are willing to do it. That is going to minimize or mitigate all your slip pretty much right there. And if I want to do you one better, you'll see some superchargers like a centrifugal supercharger. If you put that pro charger, for example, right there off the crank, then you have zero belt slip. But obviously, you can't do that with a PD blower. So that would be one disadvantage of a PD blower versus an F3 Pro Charger, for example. So there's some things to think about there as well. But all great questions, guys. Awesome. So actually, we're kind of moving to talking about bypass valves. Unless anybody has any other questions, let me know real quick. Okay. Yeah. So, hey guys, I heard we're about to 200 viewers right now. That's awesome. Thank you guys for joining in. I hope you find the information that we're providing informative and helpful. And again, to remind you, towards the end of the class, we are going to be giving away an MPVI2 to the person who answers our question first correctly. So, guys, be sure to stay tuned for that. And thank you so much. And also remember to subscribe to hptuners and also Alex to myself at Peitz Performance on Instagram and Alex Peitz YouTube channel as well. I really appreciate you guys a lot. So we're going to start talking about bypass valves. So bypass valves serve a very, very important purpose. Now, if you guys don't know what a bypass valve is, it's essentially a valve which opens with vacuum and closes with pressure. So if it sees vacuum present, it's going to open, and you're going to see inside the supercharger, if you were to take the lid off typically, you'll see a essentially a flap, which that flap will be open to allow pressure to go out into the intake as opposed to going into the engine. So when that bypass valve sees vacuum, it's pulling that valve open, and therefore that flap is open and you're not generating any boost. Once that bypass valve sees pressure against it, it shuts the bypass valve, which in turn closes that flap and allows pressure to build inside the supercharger. So at that point, then you get all the boost, you get all the horsepower, all coming right at once. So that's when you got to think about, okay, I should have probably bought a better set of tires because now you're going to be spinning, and spinning ain't winning, right? As they say. But yeah, so that's just things to think about. The bypass valve is extremely, extremely important. And also the actuation of that bypass valve. I did mention there are electronic bypass valves as well, which are pretty cool. Like on the Hellcat, for example, I'm pretty sure it's a stock SRT4 throttle body, and they convert that throttle body into a bypass valve. So they actually control the closing and opening of that valve via the ECU. So that's pretty awesome technology. So that can actually mitigate some of those surge issues that I've been talking about previously and make it a nice smooth transition. There are aftermarket companies like Smooth Boost, for example, which can do this as well on pretty much any supercharger that has a mechanical bypass valve. So that's something to think about too. If you guys already have that and you're having a surging issue, then sometimes, Grant, don't get me wrong, you can fix some of those issues with tuning a little bit, but most of the time it's more of I don't want to say a cover up, if you will, or a band aid, because that's really a negative derogatory term, but it's just not the same, right? So if you have a car that came from the factory with a PD blower, they've taken tons and tons of time, money, and effort to making that a smooth operation. When you add a PD blower to a car that never was designed to have it, you only have so much access to so many tables because you literally may not even have the table that you would need to make that smooth because the car was never designed to have it. So there's a lot of considerations there as well. So again, ways to get around it, but just want you guys to think about all the aspects of it. Now, a bypass valve also needs to be properly sized for the application. If the more pressure you make, the more power you make, typically the larger bypass valve you need. And you may see some applications with two, not in a PD blower, but in like a centrifugal supercharger, you may see two bypass valves versus just one. So just things to think about, because here's the thing. When you are full throttle and you lift off the throttle, like we did on our test, our dyno run, the car came down in RPM. Actually, we can go back to our log here just real quick. Move this out of the way. So I stayed in it until about 6,500 RPM, and I lifted. And as you guys see, the RPM started dropping pretty much immediately. That's because the pressure fell off, right? We were making 7 or 8 pounds of boost right there, which is 165 kPa, and it dropped down to 25 kPa. So it saw vacuum like that, right? So if we didn't have that bypass valve there, your RPM would have surged up and kept climbing with no bypass valve. And it could be potentially dangerous, not only for your engine, but for you as a driver. So the bypass valve is extremely important in mitigating those issues. So just keep that in mind as well. So that's pretty much the main gist of what I wanted to discuss with bypass valves. Anybody have any questions? Let me know. All right. So tuning considerations for Pd superchargers. All right. So here we are. We still have our log open, and we're going to discuss this in a little bit more detail. All right, guys. So here I am, part throttle. We still see some timing because we have no less load, so we have more timing. But once we go full throttle, which you see right here, this is relative throttle, so 86% is full throttle. Once you go full throttle, we see air fuel drop down pretty substantially. Now, as you go into higher RPM, our air fuel goes to more acceptable ranges. This being on 93 octane, we didn't go too lean on air fuel. We usually want to be 11.4, 11.3, 11.5, somewhere around there in terms of air fuel. In Lambda, it's like 0.77, 0.78 ish around there. So timing's pretty low. And also, I want to mention something about that when you're tuning a PD blower car, high loads, low RPMs are a danger zone, right? So if you see a lot of cylinder air mass, a lot of load at low RPM, you cannot put as much timing into it because the pistons will be begging for mercy. So if you've ever seen a piston after low speed pre-ignition events, it literally melts the side of the piston. And when that happens, you see a bunch of smoke come out of the tailpipe, and it's a bad day for everybody. Compression's not there, and you have to pull the motor out. We don't want any Hemi guts laying on the floor here. All right, we want happy Hemis, and we want happy engines everywhere, right? So just something to think about. So be extremely cautious when you are putting timing into these things at low RPM, high load. I'm going to go to the tune file real quick so you guys can see kind of what my spark map looks like. All right. Make sure we're on the right one. It's a 2012 Dodge Challenger SRT8 6.4 liter. Just in case you guys don't know how to do that, again, you go to Edit, Calibration Details, and that will tell you the year, make, model, and the VIN of what you're working with. Also, if you go to Controllers, you're going to see the hardware you're working with, the serial number, and the operating system ID, which is extremely helpful in certain situations. Also, we have our TCM, our Transmission Control Module. We have our serial and operating system from that. You can also add controllers as well if need be. Some pretty cool features there. All right, so let's go to the Spark map. Let's go to Engine, go to Spark, go to Advance, and let's go to Wide Open Throttle, which is the table it's going to reference once you go wide open throttle. If you notice here in this table, I have, say at 3,000 RPM and 1.4 to 1.6 grams, which is about 160% volumetric efficiency or 160% cylinder fill, we have, anywhere from 3 to 6 degrees of timing, which doesn't seem like a lot, but you don't want to put a lot in there, especially on 93 octane. Now, this engine is a little bit lower compression because it is a built motor, so it can take some more timing. Also, in addition to that, we have our cam in here. So that cam has more overlap. It has more duration. And so it's going to relieve some of the cylinder pressure, back into the intake as well, because you're going to have a little bit of reversion going on there. So the dynamic compression is going to be lower as well. So the lower the static, the lower the dynamic compression, the more timing we typically have to put into it to see ideal combustion. However, this is going to vary from application to application. This is just an example, right? So as RPM increases, our efficiency decreases, and therefore we need to advance timing. Now, this is 17 degrees on the very top end at 6,400 RPM. You'll never actually see that because we have an Iat Spark Modifier, which comes in and reduces that actual timing substantially in higher IATs, which in a scenario like we have here, you're going to have higher ITs typically a lot because it's a supercharger and your air charge temperatures are going to be higher. So actual timing at the end of the pull, now we're not bad IATs here. So our actual timing was 14.8 degrees. We only have 127 degrees IAT, but our coolant temp is about 203. So it's a little bit cooler run than what you're typically going to see on the street. So on the street, you may see 130, 140 degree IAT, depending on the ambient conditions, and your actual timing value is going to be lower and lower and lower. So your base spark values sometimes need to be a little bit higher to account for that loss in timing you'll see with higher intake air temperatures. Now, there also is an Iat Spark Modifier table, which you can adjust. So if we go back to the tune file, and we go to Spark, we go to Advanced, and we go to our Iat Hot Spark table, if it sees the Iat Hot Spark reference is 194 degrees. So this is the maximum amount of timing it can retard if it sees 194 degrees of intake air temperature. So at 2100 RPM, you guys notice actually our higher amounts of spark retard are in the lower RPM ranges. Again, that's because of low speed pre-ignition potential, and we want to mitigate those issues as much as possible with our tune. And so that's why those values are more negative at lower RPM, because higher load, lower RPM equals the danger zone for us with a Pd supercharger, right? So number one thing to think about when you're tuning for a Pd blower car is that low speed pre-ignition issue. In addition to that, you'll see, go in power enrich, we can knock our pedal threshold for voltage pretty low. Factory is about 3.7 or 3.5 volts, or something like that. And so I've got all the way down to 2 volts. So I don't want that to come into play. Basically, after I exceed 2 volts on the pedal, 0 being nothing, 5 volts being everything, after I exceed 2 volts and then other thresholds that are involved in the tune, then it goes into power enrichment. Or FAPE on this Dodge. So once it exceeds that voltage threshold, then it's going to add this value, which this isn't fuel air ratio, not air fuel ratio. So it takes this value and adds it to this value. This is our fuel air stoic, right? So to convert that to air fuel, so you can see what I mean, go 1 divided by 0.0688 equals 14.53. Right, so that is the FA or air fuel stoic for this particular application. Now that is not accounting for that, or excuse me, that is accounting for some ethanol content. But if we're thinking about this in terms of air fuel equivalent of 1 lambda, it's still going to be 14.7, but it's scaled about 3% because it was accounting for 3% of ethanol when they did the original calibration. So don't let that confuse you though. It's all good, right? So take 14.53 divided by 14.7, because that's our reference, because our wideband is spitting out air fuel ratio equivalents of 1 lambda. So we're getting it back to our language, so to speak, our dialogue or dialect, if you will. So that equals 0.988. So that's basically a correction factor you can apply to your desired air fuel ratio at wide open throttle. So if our desired air fuel ratio at wide open throttle is 11.4, we need to take 11.4, multiply that by 0.988 to give us our desired air fuel ratio for this particular application, right? So 11.4 times 0.988 equals 11.26. So that is what I call our corrected desired air fuel ratio. So now that we have that value, we need to convert that back to fuel air, right? So 1 divided by 11.26. That's going to equal 0.08880, basically. So now we have that desired fuel air ratio at wide open throttle. And now to figure out what we need to put in our FAPE table, which is an adder to our FA stoic, we need to subtract the FA stoic. So subtract 0.0688, that equals 0.020000, right? So going to our FAPE table, we are commanding 0.0200004272. So we are commanding 11.4 parts air to 1 part fuel once we exceed our wide open throttle pedal threshold of 2 volts amongst the other thresholds that are set in the tune. So just wanted to show you guys kind of how that worked on a Dodge, right? Because Dodge is different, right? So moving forward here, before I move forward, does anybody have any other questions on this? I know we just talked about a lot, and I just threw a lot at you, so please. All right, so somebody had a question about a general RPM that you look for to avoid LSPI or ways to mitigate low speed pre-ignition or LSPI in reference to RPM. So typically, it's going to depend on the engine to engine, of course, because your peak torque of your engine is going to have a pretty good bearing on that. So, your typical, yeah, it's because the cam profile, everything goes into account. But generally speaking, anything after 3,500 RPM or so on a Hemi, at least, you're going to be kind of out of that danger zone. You'll start to see the RPM, spark advance start to scale back up after that point. So, like, really, it's like idle to 3,000 RPM and 80 to 150 or higher percent load. That's really your danger zone for LSPI specifically. However, you could see it in other scenarios as well, depending on the engine, because some engines may, make peak torque later on, or they may have higher RPM ranges, and so on and so forth. But the thing about the PD blower is we're making peak torque everywhere, right? So it's always a concern, but it's even more of a concern in those lower RPM ranges. So hopefully that helps answer your question somewhat. And please let me know. All right, so moving on, guys. So keeping air charge temperatures in check. So we've really talked a lot about this already, but again, the intercooler brick, improving that as much as we can, having more capacity as well. So you may have your stock offering from different supercharger companies. Now, to improve that, you can make a bigger heat exchanger, do a different intercooler design, but that's going to be really in depth and require a lot of R&D. So typically, the heat exchanger is about the easier way to do that, and also adding a larger reservoir or an ice box. Or you do see out there they have what's called chillers, whether that be from killer chiller, FI inner chiller, active inner chiller, so on and so forth. They all kind of serve the same purpose. So basically, it's abducting the freon or refrigerant and using that, going through a chiller, and then taking your intercooler coolant, running through the chiller, and it's supercooling the supercharger coolant, which works pretty darn well as long as you have the proper fittings, you don't have any leaks, and you account for a lot of different things. It's kind of the initial install on those type of systems is kind of in depth, especially if you haven't done it before. But once you have it, they do work pretty well. I mean, granted, we saw this in the Demon as well with their particular system that they use. So even OEMs are adopting this type of method. But the thing is, you know, once you go wide open throttle, it's going to shut off the AC compressor. So you are relying on your AC compressor to do its job. So once you go wide open throttle, you may not have the AC compressor working anymore. So you are going to see a higher air charge temperature at wide open throttle. However, if you're starting the pull or your run or whatever it may be at 40 degrees intake air temperature and it raises to 70 or 80, maybe 90 or 100 at the end of the pull, that's still extremely low in reference to starting a run at 130 degrees IAT. So just keep that in mind. The ice box works really well, but you do have to run lines. You have to run a separate reservoir, usually in the trunk. So there are some things involved there. You got to run an extra pump. You gotta kick on that pump. There's some more wiring. So I mean, there are some things you have to do there. But the ice boxes work really well. They do add some weight, and if you're road racing, you may not want that weight. So there's just other things to consider there. But keeping the air charge temperatures in check is extremely important. One other method you can use is methanol injection. Methanol injection in the air charge will cool the air charge considerably, but you have to be careful because you need to wire that meth system properly. And a properly wired meth system and properly controlled meth system works really, really well. However, you do have to fill up the meth. It's a separate container you do have to fill. So there are some considerations there for a street application with your customer may not want to do that. So they might not be open to that particular method, but it is a viable solution to cooling the air charge temperatures. So hopefully that helps you guys out with that specifically. Any questions on that? All right. So brands of Pd Superchargers. There's a lot of different brands out there, and all of them have their benefits and advantages over others. And, we're not, set on one specific brand here. Uh, at Peitz Performance, for example, we sell Whipple, we sell Magnuson, we sell Harrop, we sell many different types of PD blowers, and they all serve their purpose for a particular customer. And some of them offer different things for different cars that others may not offer for different cars. So they all have their place in our awesome aftermarket world and family. And you just have to figure out which one's better for you, right? Kenny Bell has been around a long time. Whipple's been around. They've all been around a long time, really, and so they all have their advantages. And excuse me, let me take a drink here real quick. Yep. So you just really have to figure out what's best for you. And some of these, yeah, it just comes down to that, really. So if you have a Dodge, you may need a certain displacement of a supercharger that Whipple may only offer that displacement of supercharger versus another company may offer a lower displacement supercharger, which works better on your particular car or your engine. So it just really depends. So, we talked about a lot already, so we'll continue to move on. And let's talk more about roots versus twin screw. So we do have a diagram, which we pull up for you, kind of give you a little idea of what that looks like. Now, if you look at the root style supercharger, and you look at the screws in that supercharger housing, they're not nearly as, it's not much of a corkscrew effect, so to speak. It's more so taking the air in, pushing the air into the combustion chamber or into the cylinder head versus your twin screw supercharger, which has a male and a female, and it's going to more so compress the air inside the compressor housing and then push it into the engine. Now, what's better or what's worse? Well, not one's better, not one's really worse. Typically, your root style supercharger is going to be very efficient on the low end because it's just you're going to see a snappy, very instant torque gain, right? Versus the twin screw supercharger, traditionally speaking, I do stress traditionally because we're speaking in generalities right now because there are hybrid setups out there that get a little bit more in depth into how they work, which can kind of take best of both worlds scenario. But traditionally speaking, your twin screw blower is going to have more top end efficiency because it is compressing that air and it's pushing the airflow into the engine in a different manner. Now, also traditionally speaking, your twin screw supercharger is going to have a higher displacement than your root style supercharger. Like we see a lot of the Eaton assemblies, rotor assemblies, they don't go above 2.6 liters versus your a lot of your Whipples are 2.9 liter and they are a twin screw style blower. So then they go up all the way to 4.5 liters, and Kenny Bell has a 4.9 liter offering. So generally speaking, your twin screw supercharger is going to have a higher displacement, but more displacement is not necessarily better. The more displacement you have, the more pressure you make, the more heat you can potentially generate. But they can mitigate those issues with better intercooler bricks, bigger heat exchangers, more capacity, your chillers, so on and so forth, right? So just keep that in mind. Generally speaking, your Eaton rotor pack, or rotor assembly, whatever you want to call it, is going to be more thermal efficient, as we said before. And you're going to look at a lot of the OE offerings are going to offer an Eaton style supercharger with their kits, such as in the C7 Z06, you have a 1.7 liter blower, and it sounds tiny, but it's extremely efficient. It packs a very good punch for what it is. Now, the more displacement you see, typically the longer the rotor will be, the more displacement it's going to be able to offer. So it just really depends on what it is. But that 1.7 liter is extremely, extremely efficient. So, and by efficient, I mean airflow versus the airflow it can output versus the liters of displacement you're going to see. Because here's the thing, it's not all about the boost. It's all about the airflow that compressor can generate at a given RPM. So I would rather have a compressor that's making 5 pounds of boost and flowing 50 pounds per minute versus a compressor that has 10 pounds of boost flowing 50 pounds per minute. 50 pounds per minute is really what you're after. You're after that airflow. That airflow equals horsepower, right? So that's something to keep in mind, right? To give you an idea, on my C7Z06, I keep talking about it because I have a lot of experience with it, but my C7Z06, I didn't change the pulleys at all, right? I put different heads, different cam on the car. I actually lowered the boost because I improved the efficiency of the engine, and I made another 110 horsepower or so with a little bit less boost and made less heat, less temperature, and had no issues with overheating. So it just really depends on what you do, right? And also, if you don't change the pulleys to try to get all the boost out of it as possible, here's the thing, RPM is a natural power adder. If you have the airflow to supply your engine, you can keep on turning RPM, keep on making power, right? So that take advantage of the supercharger. So my car, for example, I spun to 72, 7,300 RPM, and it kept making power because I didn't try to cram a bunch of boost into it on the low end. So I generated less heat, made more power, and or more RPM. So I had to shift less, and so you went faster, right? Because shifting costs you time. Now, of course, you can put a sequential in and so a bunch of other things to accommodate for that or mitigate those problems. But when it comes down to it, the less time you spend doing other things than matting your foot to the floor, the slower you're going to go, and you're not going to win the race, right? Because we like to win the races, we like to be competitive, but you also like to have fun. And yeah, so just keep that in mind, guys. Yeah, so moving forward, unless you guys have any questions, moving forward, what's a better Pd supercharger for your car? Well, we've kind of been talking about that again natively as we've been discussing some of the ins and outs of the supercharger or the Pd Supercharger. But really, again, it's going to come down to what your budget is, what your horsepower goals are, and what fitment requirements you have for your particular engine or your particular car. You know, if you don't want to make over 600 wheel horsepower, you may be perfectly fine with a 2.3 liter Eaton supercharger, and you'll be thermally efficient. You won't have to make much power or much boost to make the power you need. But let's say you want to make 1,000 horsepower one day. Well, you're going to be overspinning that 2.3 liter blower to even try to get close to that. And in addition to that, you're going to be generating a lot of heat. You're going to have a lot of other problems and things you're going to have to take into account when going down that road. So if you want to make 1,000, well, you need to start off with a larger displacement supercharger out of the gate. Now, granted, the larger the displacement supercharger, the more things you're probably going to have to do, the more money you're going to spend, the more fuel you're going to have to supply to it, so on and so forth. So if you're trying to figure out what you need to do, you need to be realistic with yourself or realistic with your customers and explain to them, hey, if you want to make this power, you need to do this, 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 and this, right? Not to mention upgrading your transmission, axles, half shafts, whatever you may have, gearbox, driveline, drive shaft, all these other things you have to keep into account. Pcv systems, that's another good one. By PCV, I'm talking about positive crankcase ventilation. When you have a positive displacement supercharger, you're going to have more crankcase pressure. If you have more crankcase pressure, you need to mitigate that crankcase pressure by evacuating it out. The best way you can do that without having a vacuum pump on your crankcase or like a dry sump system is to run your crankcase pressure into a line pre-supercharger, because at wide open throttle, the more pressure you make, the more vacuum you're typically going to see before the throttle body. So we can use that vacuum to draw the crankcase pressure out, and also you'd want to add a catch can to that system. Now, if you just vent it to atmosphere, you can do that, but you're kind of shooting yourself in the foot because you're not taking advantage of that vacuum which is there before the supercharger. Now, some centrifugal systems are really awesome because I see like 10 or 11 pounds of vacuum, or excuse me, 10 or 11 inches of vacuum pre throttle that I can use. So if I'm pulling 10 inches, 11 inches on the crankcase, I'm going to have a lot better ring seal. So I'm going to make more power, and we're going to get rid of those contaminants from the combustion, which gets in through the engine. So we want to get rid of those contaminants as well. That's part of the purpose that your PCV system serves. So just some things to think about, guys. Anybody have any questions on any of the stuff we covered before we move on to our question and what we're all waiting for to try to get that MPVI too? Okay. Using tanks of compressed air. Um, so I wasn't, maybe there was a misunderstanding of what I was saying by compressed air. I just mean you are compressing the air inside the supercharger. So versus having ambient air coming into the engine, now you have ambient air going to the compressor housing, so to speak, and then that's compressing the air in the housing, then putting it into the engine. Now, as far as actually having a compressed air inducted, like having a separate air pump or air compressor in your engine and putting that into the engine, I don't know how that would work. I can't speak for that system, so I apologize that I can't help you more so on that specific topic. But it's the same concept, everything you talk about, right? When we talk about compressors, we have compressor maps, right? You just see this more so in turbocharged applications, but you have a compressor map, right? So you have airflow on your x-axis, on your y-axis, you're going to have pressure ratio. So there's going to be efficiency islands inside that compressor map. And so you want to be inside the efficiency islands. So if you're on the outskirts, you're not in the efficiency range, you're going to be generating heat and you're potentially going to cause more surge issues and so on and so forth. So you want to be in that efficiency range. Now, that's a little bit different than what you're talking about, but it just reminded me that I wanted to also mention that to you guys. Yep. All right, guys, we're going to get to the final stage of this, the thing we've all been waiting for. We're going to ask one question, and I hope that you guys can fill me in on this. And we have discussed it a little bit in the past in this class. So with a PD blower car, when tuning a PD blower car, and you see a loss in pressure, what is the first thing you need to check when you see that loss in pressure? Yep. I'm going to ask it one more time. When tuning a PD blower car and you see a loss in pressure, what's the first thing we need to check for when we see that loss in pressure? What's the most likely thing? All right, congratulations, Abe's very own channel. You have won the MPVI 2.0 coming at you with 2 credits loaded onto it. Be sure to email marketing@hptuners.com with your YouTube screen name and any other information you need to provide, such as shipping information, and marketing will get back to you and get you set up with your MPVI 2.0, get that coming to you. Congratulations. And for all the other guys that didn't win, you have another chance to win. Not all hope is lost. We're going to be coming live to you again, and not this coming Wednesday, but the Wednesday after that. So every other Wednesday we're going to be on, and next time we are going to be discussing centrifugal superchargers, so we can have a really good or part 2 of this segment, so we can have a really nice tie-in and get some more information to you guys. I really appreciate you guys coming and joining me for this time. And of course, if you haven't done so already, subscribe to the YouTube channel for HP Tuners. And also, I have a YouTube channel, Alex Peitz, and also my Instagram at Peitz Performance and HP Tuners Instagram at HP Tuners. And of course, follow along so we can give you all the new announcements on everything that's coming out and also our next segment coming up. Until then, I'll see you guys soon. Stay tuned.